Welcome back to this module, module 18, where we are going to discuss bounded sequence. So, the definition of bounded sequence is as follows. Let us start with the definition. A real sequence xn is bounded below if there exists an m in the set of real numbers, m is a real number, such that all the terms in this sequence xn are greater than or equal to m, that is for all n in the set of natural numbers. It is bounded above if there exists some other real number, let us call it capital M, such that xn is all the terms in this sequence xn are less than or equal to this capital M. A real sequence xn is said to be bounded if it is both bounded below and bounded above, right. So, we can alternatively say that is if there exists some capital M in the set of real numbers, such that mod of xn is less than or equal to m for all n in the set of natural numbers. Here we are taking this m to be positive, right. Alternatively, a sequence xn is bounded if the range set S, what is that? Set of all xn's for n in the set of natural numbers. This is the range set is bounded. So, we know a bounded set, the sequence, the definition of the bounded sequence can be also represented with the help of the boundedness of the corresponding set, range set. Okay. So, this is the definition of a bounded sequence. Let us come to some examples of bounded sequences. The first example is the sequence given by xn equal to the constant sequence C, 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 C and so forth, where all C are the real numbers, then it is a bounded sequence, it is bounded by C. The sequence xn is minus 1 to the power n, which is actually minus 1, 1, minus 1, 1 and so forth. This is another sequence which is bounded. It is bounded by below by minus 1 and above by plus 1, right. Let us take the third example. The sequence x n given by this time say 1 by n, it is, we know this is nothing but 1, 1 by 2, 1 by 3, 1 by 4 and so forth. It is also bounded. It is bounded below by 0 and above by 1. This is bounded below by 0, bounded below by 0 and above by 1. Another example is the sequence x n is just simply n, that is the set 1, 2, 3, 4, so forth. You can see this is bounded below by 1, but is not bounded above. There is no such capital M such that M is greater than all the natural numbers, because this is the sequence of natural numbers. So, it is not a bounded sequence. Another sequence is, suppose x n is 2 to the power n, this is 2, 4, 8 and so forth. Again this is not bounded above, even though it is bounded below, and therefore, it is not a bounded sequence, because to be a bounded sequence you need to be, it needs to be both bounded below and bounded above. Take this example, the sequence x n given by 1 by 2 to the power n, which is starting from half, half square, half cube and so forth. This is bounded below by 0 and bounded above by half. So, it is a bounded sequence. And we have the last example. This is x n given by minus 1 to the power n, 1 by 2 to the power n. This time it is minus half, 1 by 4, minus 1 by 8, 1 by 16 and so forth. This sequence is bounded below by minus half and bounded above by 1 by 4, and therefore, this is a bounded, it is a bounded sequence, it is a bounded sequence. So, you have already seen that these sequences and some of them are convergent and some of them are not. If you see that 1, 3, 6 and 7, 1, 3, 1, 2, 3, then 6 and 7, they are bounded, but out of them 2 is bounded, but as you know this is not convergent, right. So, now we state and prove a result that says that if a sequence is convergent, then it must be bounded, but the converse is not true. This can be seen from example 2. You can see here this sequence is bounded by -1 and +1, but it is not a convergent sequence. So, let us go to the theorem. So, the formal statement is every convergent sequence is bounded. Every convergent sequence is bounded. The proof goes as follows: let x n be a convergent sequence. Such that x n converges to some real number x, like this. Now, by the definition of the convergence, for each epsilon greater than 0, there exists a capital N greater than 0, such that x n minus x is less than epsilon for all n greater than equal to n. Now, take in particular epsilon to be equal to 1, and there exists some n naught for this particular value of epsilon. There exists some n naught, or you can say n naught is in the set of natural numbers, such that what happens? We have x n minus x less than epsilon for all n greater than equal to n naught. Let us call it 1. Now, then what we have? Now, if I want to estimate this x n, then I can write it as x n minus x plus x, and by triangular inequality this becomes x n minus x plus x, and by 1 this is less than, in fact this is, I have taken this to be 1. So, this is less than 1 plus mod of x, because x is a real number, x n converges to x, x is a real number. So, it is a finite number. So, this is 1 plus mod of x, and this is true for all n in n naught. That is what we have learned from here, is that if you have this sequence x 1, x 2, x 3, say x n plus 1 and so on, x n naught plus 1 and so on, then up to this should be n greater than equal to n naught. So, after n naught, these terms, they are all less than 1 plus mod of x. So, they are all less than 1 plus mod of x, it is a real number. Now, we want to see whether these terms are less than some real number or not. Because they are all finite real numbers, definitely we can find out some maximum out of it. Let m to be the maximum of this x1, x2 up to x n naught minus 1, this is the last term, and for the remaining part I take 1 plus mod of x. Then m is the maximum of these terms, the absolute values of these terms, and because all these terms are less than 1 plus mod of x, therefore I want to take m to be the maximum of these terms, right. And then what I get from this, then mod of x n is less than equal to m for all n in the set of natural numbers, and therefore the sequence x n is bounded. That is, when x n is a convergent sequence, it is also bounded. Okay. The next theorem is the following: let x n be a sequence of real numbers such that x n greater than equal to 0 for all n in the set of natural numbers, and x n is suppose convergent to x in R. Then what we should have? We must have x should also be greater than or equal to 0. The proof goes as follows: let on the contrary, let us take x to be less than 0. What happens? Let us see. Then by the property of convergence of a sequence, given epsilon greater than 0, there exists some capital N in the set of natural numbers such that x n belongs to x minus epsilon, x plus epsilon in this open interval for all n greater than equal to n. So, x n belongs to x minus epsilon, this open interval with n points x minus epsilon and x plus epsilon. In particular, because we are free to take any value for epsilon, let us take epsilon to be x by 2 minus x by 2, because x is negative. So, minus x by 2 is definitely positive. Then x minus epsilon would be 3 x by 2, which is a negative quantity, and x plus epsilon would be x by 2, which is again another negative quantity. Now, so what we have obtained, x n belongs to this open interval 3 x by 2 x by 2, where x is negative. This open interval is of the extreme points of these open intervals are negative quantities. This is impossible. Why? Because, and this is true for all n greater than equal to n. Now, you can see infinitely many x n's from the sequence are contained in a negative interval, which is not possible. Therefore, this is a contradiction. This is a contradiction, and so x must be greater than equal to 0. This completes the proof of this theorem.